2023, China's Ministry of Commerce published an export licensing requirement for two metals, gallium and germanium, that most people outside semiconductor manufacturing had never thought about. The document was 11 pages. The consequences were not. What sits on the table is not a policy instrument or an abstraction, but two physical metals that must be refined, shipped, and chemically transformed before a single transistor in a data center switches. The deepest layer of their supply chain reveals something that the surface of any finished chip conceals entirely. The restriction that was supposed to stop Chinese technology from reaching Western markets was built on a foundation of Chinese raw materials. The cuts move from the finished product backward through the wafer, through the compound, to the ore, and at each layer the same structural fact becomes more legible. At the outermost layer sits the finished chip and it gives nothing away. Nitride is the compound semiconductor of choice for high-frequency, high-power transistors. It appears in 5G radio front ends, in the power delivery stages of data center infrastructure, and in the discrete components that regulate power in high-end graphics accelerators. Germanium appears in silicon-germanium heterojunction transistors used in radar frequency analog circuits and in the optical components of fiber interconnects. Neither metal appears by name in a product data sheet. The physics of the application forces the choice of material. Compound semiconductors outperform pure silicon at high voltage, high frequency, and low noise at radio frequencies, and the engineer selecting the process technology treats the geography of the upstream supply as a variable that has already been solved before the design tool opens. The spec sheet for a gallium nitride transistor lists electron mobility and breakdown voltage. It does not list the country where the gallium was refined. It is not an oversight. It is how commodity supply chains are designed to function until they stop functioning. The 2023 licensing requirement made the omission visible for the first time at scale. The next layer down is the wafer and the fab. Taiwan Semiconductor and its peers purchased gallium nitride epitaxial wafers and silicon germanium substrates from a supply chain that sits upstream of the fabrication facility. The fab does not refine the metal. It receives a prepared substrate. The bulk of gallium used in semiconductor contexts is processed into gallium metal or gallium compounds, primarily gallium arsenide and gallium nitride, by a small number of refiners, the majority of which by volume operate in China. Refining follows a similar structure. It is recovered as a byproduct of zinc smelting and coal fly ash processing, and Chinese refining capacity accounts for a majority of global output by most industry estimates, though the precise share varies by source and year. The reason this layer is structured as it is comes down to extraction economics. Gallium is not mined directly. It is captured as a trace byproduct of processing bauxite into aluminum oxide and of zinc ore processing. The economics of byproduct capture mean that refining capacity locates where the primary metal industry is largest. China's aluminum and zinc industries are the largest in the world by volume. The gallium refining infrastructure followed the primary metal infrastructure, not any semiconductor policy. The wafer arrives at the fab carrying the record of that industrial geography in its composition, and the datasheet says nothing about it. Therein, the element itself becomes the subject, and its physical properties carry logistical consequences that no specification sheet captures. Gallium at room temperature is a soft, silvery metal with a melting point just above body temperature. It cannot be transported in bulk the way copper or aluminum travels. It is shipped as a liquid or low-temperature solid in sealed containers. Germanium is a brittle metalloid recovered in quantities measured in tons per year globally, not millions of tons, but single to low double-digit thousands, depending on the year and the source. The entire annual global germanium supply, refined and ready for semiconductor use, would fit inside a small warehouse. The rarity here is not geological scarcity. Both elements exist in the Earth's crust in measurable concentrations. The constraint is the infrastructure required to capture and refine them from diffuse, low-concentration byproduct streams. Gallium from aluminum refining makes economic sense only at the point where the aluminum is already being processed in enormous volume, in the same way that skimming cream is only efficient where the milk is already flowing at scale. Building that operation at a new location means replicating not just a refinery, but the primary industry that generates the feedstock. Every recycling program and every Western mining initiative announced since 2023 operates at a fraction of current Chinese refining capacity. The company claims and the analyst projections agree on this point, even when they disagree on timelines. The ceiling on substitution is not technical. It is the accumulated decade-scale infrastructure of smelting, byproduct capture, and chemical processing that does not relocate in response to a press release. The deepest cut reaches the export control itself, and what it exposes is not a new dependency, but a pre-existing one that had been structurally invisible. The 23 gallium and germanium export licensing requirements and the further tightening that followed in 2025 did not create the concentration. They made it legible. Prior to licensing, the flow of these materials was largely unrestricted and largely unexamined by the companies that depended on it. The licensing requirement introduced a bureaucratic choke point that the existing supply chain had no parallel structure to root around. Western efforts to develop alternative supply, announced mining projects, recycling initiatives, allied nation sourcing agreements are at various stages of development, but no independent benchmark confirms that any alternative source currently operates at a scale sufficient to replace Chinese refining for either metal. The company claims are optimistic. The analyst estimates are more cautious. The physical infrastructure is what it is. Gallium and germanium did not become choke points because someone targeted them strategically from the beginning. It's because Western chip economics systematically underpriced the risk of geographic concentration in upstream materials. The same logic that made just-in-time manufacturing efficient also made it fragile. The export controls on advanced lithography equipment and chip design tools were constructed on the assumption that controlling the manufacturing end of the chain would be sufficient. The gallium and germanium licensing revealed that the chain has another end, further upstream, that the control architecture did not address. There are layers this dissection cannot settle. The precise share of global gallium and germanium refining that Chinese facilities represent shifts with production data that is not uniformly reported or independently verified. Figures cited in policy documents and those cited in industry analysis differ enough that precision here would be false precision. Western alternative supply to reach meaningful scale is genuinely contested. Mining and refining projects have announced timelines that have previously slipped, and the physical infrastructure required is not in question, but the pace is. Whether the 2025 tightening of export controls represents a durable strategic posture or a negotiating instrument with potential release points is not visible in the materials themselves. It is a policy question that the teardown of the supply chain cannot answer. What the analysis can settle is structural. The dependency exists. It is material rather than regulatory in origin, and the substitution ceiling is real even if its precise height remains uncertain. The supply chain, examined layer by layer, does not require optimistic or pessimistic assumptions to reveal its shape. The shape is the finding. This dissection are limits of data granularity and policy legibility, not limits of the structural observation. The material dependency runs in the opposite direction from the chip control architecture, and that fact holds regardless of which quarterly production figure turns out to be accurate. What the full dissection shows is that the semiconductor supply chain has two ends, and the control effort has concentrated on one of them. The finished chip is the visible object. The refined metal is the invisible precondition. Gallium and germanium are not strategic because someone decided to make them strategic. They are strategic because the physics of high-frequency electronics required them, the economics of byproduct refining concentrated their production, and the policy architecture that was supposed to contain Chinese chip development was designed looking downstream while the upstream ran in the other direction. India ships, the wafer that Taiwan Semiconductor processes, the transistor that switches inside a data center accelerator, each of these objects carries in its material composition the record of where its inputs were refined. The export license made that record visible. The constraint was not new, the visibility was. The restriction and the dependency it exposed were written into the supply chain long before the licensing document was signed. What object should we open next? If there is a specific chip, a process node, a system, or a material you want to see taken apart layer by layer, leave it in the comments and we will put it on the table. If this kind of dissection is what you came for, subscribe and turn on notifications so you do not miss the next cut.